So in this talk, I want to talk about towards semantic understanding of mobility data. I'm from Penn State University. I'm an assistant professor there. And so I will start with first mining mobility data, then talk about why I feel what I feel is the limitation of the current work, then further move on to the towards semantic understanding. Okay, so I have been doing mining mobility data for quite a while, since I was a PhD student. And this mobility, basically, most of the work I've done is on the trajectory data. Trajectory data is quite a simple format of data. It's basically a sequence of timestamps and locations. Right? So suppose you are tracking someone, then you have a timestamp, and you have a GPS location on the map. So you can track a lot of different kind of things. You can track human, vehicles, animals, airplane, or even like hurricane traces. Right? So you get a lot of trajectory data. And so there are many, many applications in using the trajectory data or mobility data. So I just name a few. So first, if we have a lot of human movements data, especially now with the wide usage of the mobile phone. In US right now, by the end of last year, we have about 64% of all mobile subscribers are using smartphones. And if you know, smartphones actually are all secretly tracking all your location, no matter it's Apple or Android. So it's actually constantly sampling your location. So actually they know where you are. Definitely for the business side, the good thing is they can better profile your interest based on where you actually go, the physical activities you have. On the other side, there are also very interesting collaborations. For example, I have a project I collab with a social scientist at Penn State. So our project basically collected many human movements in Chicago. They have lower socioeconomic status. And also they have some health problems, for example, diabetes. So we basically, that was an NIH project, and we want to see what is the correlation between the places you frequently go and also your health and the socioeconomic status. And for example, do you frequently go to fast food, or you have no access to very good grocery store? So that was the idea. So based on your physical movement and see the correlation with your health or socioeconomic status. So that is human movements, and definitely we can also analyze the vehicle trajectories. Nowadays we have a lot of public data set. Probably many of you already know that New York City released almost all the yellow taxi data. It's about 500,000 trips per day, which is a huge amount of data. And definitely there's a lot of things you can do once you have this data, for example, like traffic prediction and control, or you can do like a better travel time estimation. And definitely you can also see, like you did a lot of work in this direction, is the how does this traffic correlate with noise, city noise, or air pollution. Right, so another part, probably a little bit off from the urban part, but I did a lot of work on this when I was a PhD student. I collaborated with the animal scientists, and they have the animal movement traces. It's also a very good frontier in the animal science domain as well. They now put the GPS tracker on animals to track how do they move. Why do I call this is a frontier? Because it actually need a very good technology to support that. Imagine if you want to track like an eagle, like migrate, like a very big bird migrate from, say, North America to Argentina, right? So one of the biggest concern is like they need to have very good battery, because you cannot charge battery for the bird when they start flying. So actually there's a technology bottleneck. But now with the advancement of the technology, the battery can sustain much longer. So they can track a bird without charging the battery for several years and see the migration path, and also see how the environmental changes change the migration path. So that is also very frontier research in the animal science part. And also definitely there's a lot of disease transmission from the animal to human, and that really relates to how animals move and how do they contact with people. So there are many applications, and I just name a few. We developed data mining techniques to discover the patterns from the trajectory data. Okay, so I will basically, the outline of the talk today, I will first talk about some of our existing work on mining the mobility trajectory data. And I do want to really highlight what is the limitation of those work. Then I want to move towards talking about mining mobility data in context. Basically, it's towards a more semantic understanding of the patterns by using external data. So lastly, I will talk about applications of mobility data. We have a KDD paper on this using mobility data to better predict the crime. Okay, so I will start with the first one, mining the mobility pattern. So after doing this mobility data analysis for quite a few years, I think how one individual trajectory is generated, probably there's three very key factors that generate an individual trajectory. So one of the most important one definitely is the self-routine behavior, right? So you go to work every day, go back home like after work. So this routine behavior probably dominates 90% of your trajectory. Okay, but then besides that, the other two key components is your relationship with other people. So for example, you maybe you hang out with a friends for tonight's dinner because your friends is there, or you go back to your hometown to visit your family during the holidays because your family is there. So that's more because you make such movement because of the social interactions. Right, so the last part is, besides the interaction with other moving objects, you also have sort of correlation with the external context. External context here means, for example, here's a conference. So we are all here coming for a conference. If there's a baseball game tonight in AT&T Park, probably some of you will go to the AT&T Park to watch that baseball game. So that is more like you make this movement because there's some external context. Right? So I want to categorize in these three directions because one direction you only need one individual data. You can study the routine behavior. And the second one, you need other moving objects data. So it's more like a collection of trajectories. You study the relationships. And the third key component is you do not only need the trajectory data, but you also need external context data to understand the trajectory. So I've done quite a few work in all these three directions. I will skip the periodic behaviors. We have some KDD papers on that. If you're interested, you can refer to our KDD papers. But I will talk more on the relationship detection we did mostly in recent years. Okay, so basically the relationship detection is I give you two trajectories of two moving objects. You want to determine what is their relationship. Or maybe the first question we can ask is giving two movements. Say we have two trajectories here, like R moves like this and S moves like this. And each of this is like a timestamp, the location. And the first question we could probably ask is, given two trajectories, what is the relationship strength? Right, so can anyone give me a simple answer? If I have your trajectory and I have my trajectory, or your friend's trajectory or something, like what is the most straightforward way to measure the relationship strength? Yes? Collocation? Yes? Destination? Based on the destination? What do you mean based on destination? Okay. Final destination? Okay. Okay, that was the answer I never got before. So, but collocation probably, because Fosco is the person who did a lot of trajectory analysis, so you know collocation is one of the most frequent measure we use. What is collocation? Basically, is we look at how many timestamps we're physically close, right? So that's collocate. Like we collocate the same location at the same time. So if we collocate multiple times today, probably we have a stronger relationship. So that's a very typical method to measure the strength of two trajectories. Okay, but I think that's definitely has problem. Otherwise, we won't have recent papers on this. So can anyone think about what is the problem of simply doing the collocation frequency? So basically, I'm saying we are making this assumption, the more frequently you co-locate with another person, the stronger the relationship is. But the less frequently you co-locate, the weaker the relationship is. And do you all agree with this assumption?
Depends on the density of the place where they are co-located. If they're in like a subway or something.
Yeah, exactly. So you are suggesting it really depends on the location we meet, right? So if we meet at Subway or meet in Central Park, maybe we don't really know each other. So it doesn't mean too much. That's a very good point. Yeah, and also how many time, like what is the duration we spend the time together? Yeah, so basically, these are all very good points. So our basic idea is like you have to look at details like how long, and it's more like when and where you meet, and what is the semantic meaning of meeting at that location. So that goes back to the semantic meaning. But so far we talk about semantic meaning, we don't really use external context yet. We'll talk about that later. But semantic meaning, just give you a better example. So suppose this is where I am. This is where Penn State is. I guess most of you don't know where Penn State is. So this is Pennsylvania State, and we're right in the middle. And here is like Philadelphia, and here is Washington, D.C., and CMU, Pittsburgh, is right here. So we are really in the middle of nowhere. So but you're welcome to stop by sometime, because we are on the way from Pittsburgh to New York. Okay, so if you're making a trip from CMU to NYU or Columbia, so stop by Penn State sometime. So anyway, so this is where we are, right here. So you can see like this is State College and these two big cities. So this is just toy example. So say last month, for example, most of my time I spent in State College, but I made 2 trips last month, once to Washington, D.C., and another time I went to Philadelphia. So it's 2 different day trips. And suppose you look at another person, right? Suppose I met exactly the same person. I met this guy in Washington, D.C. during my trip to D.C., and I met the same guy in Philadelphia again. So do you think that's a coincidence? Yes. Why is that? But if it's not a coincidence, that means we definitely have certain relationship, right? Because the probability of meeting exactly the same person at different 2 locations, especially none of this is my living location, then the chance is very low. So basically the idea is like if you're meeting with someone like you have very low probability, then maybe that indicates you have very strong relationship with this person, even though you don't co-locate with him that often. Okay, but on the other hand, let's say this random guy in State College, I may frequently run into this person, say we just ran into each other in a restaurant or in the office building, but maybe I have no idea who the person is, but I just happen to run into him every day because we live in the same town. So compare with this person, even if we meet that frequently, we don't really have any strong relationship. But the person we meet here, even though I only met with him 2 days, is a very strong relationship. Actually, this is just a real case because I went to DC for a workshop, then met with some guy there. Then after a week, he invited me to go to Philadelphia to give a talk. So it is actually a real case. Okay, so we do have certain correlation because I really know this person. So my whole point is, maybe I meet with a random person many, many times, but it doesn't really, but this is expected because our background is very similar because we're both State College residents. So the chances we meet with each other is very high. So even we meet very often, it doesn't mean too much. Okay, compare with the other person because we live in total different cities. That guy lives in Philadelphia. So the chance we meet each other at these 2 locations is very low. So actually, I have a much stronger relationship with this person compared with the other random person. And this is our VODB paper in 2014. So I guess many of you will ask the question, then how do you evaluate results? You know, like human mobility usually have a lot of privacy. So I was very fortunate to collaborate with animal scientists, and the animals don't have a privacy issue. Probably they do, but they don't. We don't know. So anyway, so we use this data of animal data. So there's not too much animal privacy in this issue. And so this is the Panama Island in Caribbean. And this data I work with animal scientists that collected the trajectories for 12 Panama monkeys. It looks like this, really cute. So they collected data for like half a year, look at the GPS traces. And by using I actually skipped a lot of algorithm, but based on using our method, we can basically draw a social network graph. And if it's like a green line connecting two nodes, so each node is one monkey, because we have like 12 monkeys here. So if it's a green line, that means these two monkeys, they have a significant attraction relationship. That means they meet more often than expected. Okay, and one benefit of our method is we can also detect avoidance relationship. So those red lines means they have avoidance relationship. That means these two monkeys meet less often than expected. Okay, just give you a better illustration for some group. Because there are 12 monkeys, they belong to 6 groups. Each group has 2 monkeys. So if you talk about within one group, it's not really interesting, because definitely they have a very strong attraction relationship. They move together all the time. So it's more interesting to look at the cross-group relationship, right? So I picked these two, and you can see all these two, they have pairwise, very significant attraction relationship. And this group here, and also group here. Probably people in the back, is really hard to see. But these two groups have very small overlap in the territories. So each of these is a territory of the movement. So you can see these two groups, they have very small overlap in the territory, but they still meet very often. So for some reason, they will go to this location at the same time and meet there. So they have a strong attraction relationship. We don't know why. I talked with the animal scientists. It could be there's some food resources there, and it's timely sensitive food resources. So it only shows up for a certain time. And these two groups are very peaceful, so they just go there at the same time and get the food. But anyway, they meet more often in this very small overlapped area than expected. However, if you look at this, the same yellow one and the blue one here, they have much, much larger overlap. And it almost takes almost half of the territory of the yellow group. But they meet very, very infrequently. So they rarely meet, co-locate, go to that overlapping area at the same time. So the animal scientists say, actually, whenever they meet, they run into fight. So they observe several fights between these two groups. So probably, even though they have a lot of overlapped area, they try to avoid it with each other. Okay, so that was the basic idea of this paper. But again, I want to highlight the limitation of this work. As I just mentioned, you have attraction relationship, but you don't know whether you're attracted by each other or you're just attracted by a third factor, right? So I just said probably because of the food resource there, so attract both groups to go there. We don't really want to be friends with each other, but it's just like it's happened to we have the same interest. Or say there's a football game or a baseball game, we just happen to go at the same time, but we don't really know each other. So the third factor, how to capture it, very few work has done that because we need external sources to look at that information. So I feel that is basic limitation of this work. And follow up on this work, we further did some more about the relationship one. This is our ICDM paper in 2014. And this is actually a Central Park example. So the first one, we only look at whether we meet at the location I frequently go to, right? But I don't look at how about the crowd. So this one is more like if we meet at a very crowded location in like near Central Park, probably it doesn't mean anything. Okay, so compare with like we meet in another place, even more middle of nowhere, Kansas, right? So right here, maybe not too many people co-locate there, but we meet there very often, then that means something. So basically, we want to look at the location, whether it's popular or not. So that was the idea of this paper. And this paper, we didn't use the animal movements data. We used the geotag. I think it was a Goala data, was a location-based social network data. And we saw by considering the personal background, global background, it can significantly improve the prediction of your online friendship. Okay, so that was the relationship one. There's one more relationship one I want to briefly talk about. I'm going to skip all the technical details. So this is our ICDM 2013 paper, and we look at the follower and leader relationship. So let's see when I can play this. And again, this is a collaboration with animal scientists. If you see the traces animation here, you can see the blue one is basically chasing after the red one. And you see all the way here. So red one is always the one who is leading the movement. So this one, we want to basically detect who is the leader in the group when they move, who is the one who leads the whole group. Okay. But why do I want to mention this? Because first time I showed this to the animal scientists, the first question they ask is, where did it happen? Okay, because they say, if it happened just near like their territories, it doesn't mean too much. They're just playing around, right? They're just chasing after each other. It doesn't mean anything. Okay, but if it happens at a location, well, at the boundary of their territories, when they try to invade the other group, then that means something. That is the true leader, only when they're going to fight. So basically, they ask the question, they move like this, where did it happen? Okay, it's more like play around, or it's like a real leader. So it begs to the question, we need to look at the context. Otherwise, we detect these kind of patterns, the leaders maybe just like, it doesn't mean too much. Okay, it's not really the true leader. So based on these several works, I see the biggest limitation is we didn't consider the external context. In this work, as I just mentioned, in the VLDB work, we didn't look at external resources. And also in this, even in this geotag trees work, we didn't look at, for example, we look into one mistakes we made by our algorithm. These two persons meet very often, but they're not friends. Then we realized they often go to this music, like this park has a lot of music events in the summer. They just go there at the same time to attend the events, but they're not online friends. So that is the mistake we make because we didn't use any of the external information. But if this is like a private residential area, probably means these two persons has very close relationship, right? Okay, so the same as this one I just mentioned, the true leader and maybe the trivial leader. So how to differentiate between these two. So I talk about this work, I basically want to highlight, I feel the biggest limitation so far is we often ignore the context of where it happens. Okay, then that really gives us a lot of limitation in semantically understand the trajectory patterns. That's why in our recent work, we try to focus more of mining mobility data in context. So we want to consider external data to better understand the trajectory. Okay, so it goes to our third part here. And what do I mean by external data? So I feel many of the existing work has been focused on the trajectory data only. And we want to further consider, say, the point of interest, the event data, the net type, or the weather, or this type of data. One very fundamental question in semantic data mining, semantic trajectory data mining is probably it's like I give you a raw trajectory traces. It's at this time, at this, I'm at this location, right? So you want to infer what is a semantic. The ultimate semantic will be, this is actually Penn State again. I'm at Beaver Stadium. So here is a POI, which is the Beaver Stadium, point of interest, the POI. And I'm actually visiting Beaver Stadium for a Penn State football game. Okay, so this has two layers. The first layer is giving your GPS location. You need to know I'm actually visiting Beaver Stadium, not a coffee shop or an office building nearby. Because also there's noise in the GPS positioning, right? So you want to know this actual GPS location match with the point of interest I'm actually visiting. So the second thing is even harder is not only I'm visiting this location, you need to tell me I'm visiting this location for work or I'm visiting this location to watch a Penn State football game. So basically, we want to, from the raw location traces, we want to know the ultimate semantics of this location movement. Okay, so we recently have 2 papers on this, and this is our very recent paper just accepted by CIKM. And so the idea was, if I'm here at a location, how to match with the actual destination you go. Suppose this is your GPS location. Did you actually go to a clothing store or you go to a restaurant? So basically, you try to give a GPS location to associate with the actual venue. And I'm going to skip a lot of technical details. If you're interested, you can refer to the paper. But the very basic idea is, if you imagine how to do this problem, so we are all here. How do you know, like I'm visiting like a KDD and another person is actually working here, right? So you basically look at the history, right? So that's the idea. So if the other person actually come here on a regular basis and stay here for quite long, so he is very unlikely to attend the KDD conference. But if for you, you've been to many academic affiliated location and also event, so it's more likely for you is actually coming for the KDD conference. So the basic idea is we think there's some hidden interest that dominate kind of determine which actual location you go. So we use a Markov random field to maximize the consistency in this interest. Okay, so that was the idea. So I'm not going to talk about a lot of jargons here, but basically we assume there's some interest and there should be consistency in the interest, and we maximize that interest. So just give you some results. So for example, this person, this is from geotag trees data. So suppose I have several observations at different locations, and those places are the venues. So most straightforward way is each location you match with the closest venue, right? But that doesn't consider the interest. So then we further consider there's consistency in the interest. We discover this person is interested in going to a coffee in the afternoon. So then we can correct those mismatches with the wrong location. Most of this location, actually, the ground truth should be going to the coffee in the afternoon. Even though the coffee are different locations, but we can better do the annotation, do the matching because we discover the interest. And I also want to mention all of this is unsupervised. So it's different from recommendation system because we need some previous knowledge about this person, where the person go. All of this is just unsupervised. So based on all the raw GPS records, we want to associate with the ground truth destination. Okay. So another one I want to quickly talk about, this is a paper last year. And the previous one, we were trying to match with the actual destination. So this one, we try to annotate which event the person actually go. So we give 2 data. One data is the GPS traces. Another one is the geotag trees. And we basically use some methods. So eventually, we can annotate when you're at this location, what are you doing? So I'm just showing some results. So suppose this person is in the Manhattan several times. So we can do the annotation for this location. The top keywords of this location is garden, Madison Square. So basically, Madison Square Garden and Rangers and Penguins. So basically, by annotating that GPS location, we know this person, sort of you can infer he is at Madison Square Garden watching a game between Rangers and Penguins, right? So another location, we have similar words, and but different terms, like NYR stands for New York Rangers. Compared with just like a POI, simple annotation, we don't really know, even though the top one is Madison Square Garden, but we don't know which event the person is attending. So by doing this, we can better profile the interests of this person more dynamically. So we know, actually for this person, he has been to several locations, all have sports events. So this is really a sports fan. So based on annotation of the locations, we can better understand the interest of the person. Okay, so these are just 2 pieces of our recent work on towards more semantic understanding of the mobility data. And so lastly, I just want to quickly talk about this. If you have time, stop by our poster session tomorrow evening. I want to talk about application of mobility data. Definitely has a lot of application, but I just want to first talk about this one in our KDD work this year. We basically try to use the newer type of data to better understand the crime. So new type of data. So what is the traditional data? First of all, so this one also we collaborate with the criminologists. So the traditional data they use basically two. One is the demographic data, as I just mentioned in the earlier session. So basically demographic data tells you what is the race, income, disadvantage index, all this information about the residents in this location. So they use this data and see the correlation with the crime rate, whether it's high crime or low crime, right? Another part they use is called the geographic influence, and that's quite straightforward. If the nearby location is not safe, then this location is not safe. So basically, it's like geographic. If we're geographically close, definitely we have similar property. So that was the idea of this one. And then the traditional features. But actually, what we propose to use is quite a thought to them is quite modern data. So one data we use is actually Christina was talking about is the point of interest data we got from Foursquare. And that data significantly improved the results. So the basic idea is the point of interest of data can tell you the function of the locations, right, which is not captured in the demographic data that only tells you the properties of the residents. Right, for example, the point of interest will tell you this location has a lot of restaurants, has a lot of clubs, has a lot of transit center, has a big transit center, and can even tell you the popularity of those venues. And those are very useful information to tell you the function of this location. As I also just talking about in earlier session, is we saw if, for example, very famous, not famous, a very interesting example in our data is in the Chicago airport. Let me see whether I have a Chicago map. If you have ever been to Chicago, this is Chicago airport, which is quite isolated from the rest part of Chicago, and there are not many residents there. So if you use the demographic information or use the geographic influence, you're going to say Chicago actually has an airport part neighborhood has very low crime, but actually it's not. So airport area actually has quite high crime. So on one side, because it's a big transit center, on the other side actually has a very frequent commute, right? So that's one type of data is the point of interest data we use. The second data we use is the taxi data. As I just mentioned, there's a lot of public taxi data right now. And why we think taxi data is new? Because think about this. You may commute from your work, from your home to work, and these two locations could be far away, right? Maybe a 30 minutes drive. But so they are not geographically close, but these two locations probably have similar properties, because otherwise you won't choose to work there and live there. And people who go to work, we influence each other, right? So it's not you're not only influenced by people who live close to you, you're also influenced by the people who are at the same working place. So that's why we think this commuting sort of serves as a hyperlink on the map that can tell you the correlation between two locations. That's another case we just mentioned for the Chicago airport, even though it looks isolated from the rest of the Chicago area, but it's actually highly correlated with the downtown area, because there's a huge amount of commute between Chicago airport area to the downtown area. Okay, so basically we use the different types of data, and we show by using all of the data, the best we can get the best performance. By using each of the individual data, we can also get a very good performance. One thing I do want to point out, I think is something also very interesting. So if you use the demographic data, the relative error will be 0.335. But if you use demographic and also geographic influence, which means the nearby, if nearby is not safe, this location is safe, actually the improvement is very, very marginal. So can anyone guess why? So if you use demographic data, you already achieve pretty reasonable performance.
Because the two are correlated.
Exactly. So these two information actually they're quite correlated. So it's a little bit redundant, right? Because the nearby location probably have the similar demographics as well. So actually these two information are a little bit redundant. But the POI information and the taxi data, they're not redundant. And they really improve the performance on top of each other. Okay. So that's probably basically I want to talk about. And then I think that's the last piece. Is it almost the time, the chair?
Yeah, we still have some 10 minutes.
Okay, so I just want to summarize. So our work is mostly supported by NSF, and these are all my collaborators and my students. I'm very passionate about interdisciplinary work. So you see, I collaborate with the animal scientists, I collaborate with social scientists, and also criminologists. So I just want to, maybe the takeaway point is there's a lot of, there have been a lot of work in mining the trajectory data. But I think now the focus should be switched to more by using all the data we have, using more of different data, maybe even collect from different domains, and how to, I think you also just mentioned this, is how to really fuse the data from different domains together to help us better understand each other, because it is all one unified ecosystem, right? So everything is actually correlated with each other. So if we really want to semantically understand the trajectory, we have to use the external context. Okay, so that's it. Thank you.